let's do a brief review of what we discussed last time. So the focus of last lecture was to get you ready for VAEs. There was a summary slide. Okay. So we defined a couple of terminologies and useful mathematical identities and lower bounds. So first off, P of Z is what we design. It's our design choice of what we want to sample from during inference. So mostly used choice is standard normal distribution or uniform distribution. And we had this encoder and decoder. So P of X given Z is a decoder network, and P theta of X is how we're going to approximate the true data distribution, P theta of X. This is the analytic form for this is not given. We can only sample from this distribution. I mean, we don't know how it looks like. So we want to approximate this with P theta of X, but turns out this integral has this thing inside, P theta X given Z, but this analytic integral is intractable because this guy is nonlinear, has CILU, exponentiation, and all the complicated stuff. So we cannot actually integrate this. So we introduced, and if you apply base rule to P of X given Z, it's related to this true posterior P of Z given X. And by same logic, since this guy is intractable, this guy is also intractable. So our solution was to approximate P theta of X with a neural network Q, which we call variational posterior. And this turns out to be the encoder. So upon receiving X as input, so remember, when you condition on something, this is no longer random. So we fix X, and then this encoder network will output parameters that defines distribution on Z given X. From that distribution, we're going to sample Z. And when we sample Z, we pass it through the decoder, which outputs parameters that defines X given Z, the conditional distribution of X given Z, and then we can sample X hat. And some of the useful mathematical tools was we discussed KL divergence between two probability distributions. And turns out when the two distributions are Gaussian, then we have a closed form solution for KL divergence. And we also talked about Jensen's inequality and talked about non-negativity of KL divergence. And I think that was pretty much it. And the reconstruction loss can be interpreted as, so minimizing the MSE loss could be interpreted as maximizing the log likelihood under the Gaussian model. Okay, so let's get started. So today, hopefully, we're going to finish VAEs. So last time we talked about learning latent representation Z, where dimension of Z is a lot less than X. And we could use vanilla autoencoders if you just want to do feature succession here, or if we want to do other unsupervised learning task. But the problem was if you want to do generation, then it's problematic because A is map Z to undefined space, so it gets mapped here and there. But during inference, we would like to sample from predefined design distribution that's easy to sample from. So we would like axes to get mapped to a distribution that's very close to what we want to sample from. So we talked about various mathematical tools like KL divergence between two distributions, Jensen's inequality, KL divergence between Gaussian specifically. So we spent quite a lot of time discussing these tools and giving you some intuitions. So today we're going to discuss VAEs. So how do we put a probabilistic spin to autoencoders? So given some data X, we pass it through our variational posterior encoder. And this defines distribution on Z conditioned on X. And then we're going to sample Z here, pass it to the decoder. This is going to define a distribution on X given Z. And we're going to sample X hat. But so we're going to be specific, but this is just a picture. So to be super precise, during training, we don't sample X hat. During training, we only care about maximizing the negative log likelihood. So in fact, we don't need to sample anything. We take this guy, push it here inside, measure the height. That's what we want to maximize. Okay, that's maximizing the log likelihood, right? And then we have this penalty term that regularizes this variational posterior being too far off from our sampling distribution. And the elbow evidence lower bound was it's composed of two terms: the reconstruction error, reconstruction fidelity, and some form of regularization that penalizes this distribution deviating too much from PZ. Okay, so yeah, before we actually derive elbow, just some more background. We talked about these pretty much last time, but so what is the maximum likelihood objective? So like we saw in the previous case, a generative model assigns probability to data, and given some data points from this distribution that we don't know how it looks like, but only have access to samples, we want to learn a parameter that mimics this distribution. So that's our model, P theta. So in latent variable generative models, we want to introduce a hidden variable Z, and it influences the generative process of X. So during the generation process, we sample from our prior distribution and pass it as input to the decoder network and generate a sample. So this decoder network defines a distribution on X given Z, and we sample from this. That's going to be generated sample. And for the decoder network, for continuous data, we usually use this form of Gaussian model, where neural network outputs the mean parameter of this Gaussian, and typically the standard deviation is fixed as constant. For binary data, we'll use Bernoulli model, where pi theta defines the parameter for Bernoulli. So this parameter in Bernoulli distribution is the probability of flipping head in a biased coin toss, right? So, okay, so given the data points, given the samples here, we want to maximize the log likelihood. But turns out, under this latent variable model, we need to marginalize out this nuisance variable. And this is complicated because this part is nonlinear. And this integral is generally analytically intractable. So we need to find a different way to maximize this. So how do we do this? So let's look at this more closely. P of x given z by base rule that's related to the posterior P of z given x. And this denominator is again our likelihood term. So turns out true posterior is also intractable by the same logic. So we would like to approximate this with a neural network Q. So we already talked about why vanilla autoencoder might not be optimal for inference, for generation. It could leave some holes in the latent space, and that's not going to generate meaningful images. We drew a picture last time. We could end up sampling from here, and pretty much nothing was generated here during the training process. So the reconstruction quality, not necessarily reconstruction. The generation quality might not be so good. Okay, so this was our block diagram view of the probabilistic version of autoencoders. So given x, this sample, push it through the encoder here, and outputs a distribution of z given x. Sample z, push it through the decoder, outputs a distribution on x given z, which then we can sample x hat from, right? Okay, so, and also we wanted the encoder to follow our inference time sampling distribution. So let's look at closely what's inside the encoder and decoder. So far this has been a black box, so let's crack it open. Okay, so the role of the encoder is to approximate our intractable variational posterior, and it's usually designed like this. It has a neural network that receives x, outputs the mean parameter of the Gaussian distribution of z given x, and it could also, the network could output two things. So it could output the mean and variance parameter that completely defines the Gaussian distribution. Sometimes you do this, sometimes this is just constant output, depending on how you design it. And for numerical stability, we typically, when we decide to output a standard deviation, we take the log, we output the log of the variance to make it more numerically stable. So if we have this guy and this guy, like the equation here, this completely defines the distribution, which then we can sample, right? So this is distribution on x given x, sorry, z given x, where the mean parameter is a function of x. And the variance parameter is also function of x, which then we can sample the z's. Right? This is what's inside this encoder network black box. It's a neural network. It turns out to be a neural network that takes as input x and outputs all the necessary parameters that define the distribution. Okay? So that's the encoder. How about the decoder? So pretty much similar. So it receives z, and outputs this, the parameters that define the distribution x given z. So for continuous data, we would like to use Gaussian. For binary, we could use Bernoulli, but you don't have to. You can decide your own distribution. And I already talked about this. During training, we don't need to sample x hat from the decoder. We just need to evaluate. So just to draw the same figure again. We just need to evaluate the likelihood of the data. That's the input x that was inputted all the way back into the encoder. We take this guy, evaluate its likelihood. Okay? That's what this term means. We want this to go as high as possible. Okay, so here is the block diagram view of what's different during training and generation. So during training, we sample a batch of data x, pass it through the encoder, sample z, pass it through the decoder, and this defines the elbow loss. There's also loss contribution from the encoder as well. KL loss. And during generation, we sample the z's straight from our design sample distribution. Okay, we sample z from standard normal distribution, pass it through our decoder network, and we sample some data from it. All right? So during generation, encoder is no longer needed. This component here is useless during generation. Okay, so there was plenty of intuition. I don't know. Personally, I rather just see the equation and derive it, and then give intuition. That's what we done, I think, in the last year. But ChatGPT recommended that I give lots of block diagrams and intuition first. So I decided to follow ChatGPT's advice this year. But previous year, we started from here. From log likelihood, and derived the equation first, and then gave intuition. Okay, so yeah, what's our goal? We want to maximize the log likelihood under our model. So P theta of x is our model that models the true data generating distribution, and turns out this involves an integral over all possible z's, which is intractable because this guy has inside Silu, ReLU, and etc. So what we want to do instead is we want to derive tractable lower bound and sample X, compute the lower bound, maximize the lower bound with respect to these parameters, encoded equal parameters, sample another batch of X, reevaluate the elbow, maximize the elbow with respect to the parameters, and repeat. That's the process. Elbow stands for, like I said, evidence lower bound. Okay, so let's set aside all the intuitions and block diagrams, erase it from our head for a little bit, and just think about equation only. Okay, so our goal is to maximize the log likelihood. And here, this is we need to integrate out or marginalize out this nuisance variable z. So we're going to multiply and divide by same distribution. So far, nothing changed. Okay, so equivalently, we're going to rewrite this part here as expectation of random variable z under Q distribution. Okay, so far just massaging the equation, nothing changed. No approximations, just pure equation massaging. Okay, now we're going to invoke Jensen's inequality. So for this log function, which is concave, log of expectation of random variable is lower bounded by expectation of the log of the random variable. So let's call this equation 1. This is equation 1 again. Just copy pasted. All right, so I'm just going to swap the order of log and expectation and use inequality here through Jensen's inequality. Okay, and I'm going to call this guy as elbow. Okay. Let's just give it a name. So this is equation number 2. So what I'm going to do next is apply Bayes' rule, or definition of conditional distribution. So from this joint distribution of x and z, I'm going to rewrite this as probability of the x given z times p of z. So this is just definition of conditional distribution. So this part just changed from 2, numerator. 2 became 2.1. Okay, by property of the log, I'm just gonna break this into different pieces. Okay, so this piece here, I'm gonna take it out here, and the rest came here. Okay. All right. So now it looks obvious. This guy is a reconstruction slash log likelihood. This component is the definition of KL divergence between negative KL between this guy and this guy. This just definition of KL divergence. Okay, so elbow has the likelihood term and the KL divergence term. So first thing, first term, it encourages good reconstruction, right? So the execution order, that's important, right? First, you sample Z. Well, actually, this is number 2. Number 1 is you need to sample X from your data set. It gets inserted into our encoder. Now we can sample Z from the encoder. Number 3, we pass this Z to the decoder. And number 4, we evaluate the probability of the original X here. And we like to increase the probability density assigned to our original X. That's what this term does. So if we increase elbow, increases the reconstruction, decrease the KL divergence between our variational posterior and our sampling distribution. How about the second term? Like I just said, variational posterior should stay close to our sampling distribution. Otherwise, it's going to get penalized because we're trying to increase elbow. So reconstruction quality goes up, KL divergence goes down because of negative sign here. All right, that was clean. So it's easy to show. So elbow was a lower bound, right? So because we used the Jansen's inequality here. So you can start from 1 and massage it so that elbow pops out plus some leftover term. So maybe you can do this at your own as your own exercise. So massage 1, equation 1 here. Don't use Jansen's inequality because that's going to give you a lower bound. So with equality, you can show this log likelihood is equal to elbow plus some garbage. Well, perhaps I shouldn't say garbage, some leftover. What is that leftover term? If we inspect what's inside here, this might give us some intuition about the gap between our true objective and our surrogate objective. Turns out the exact difference between the elbow and log likelihood is this guy. It's KL divergence between the variational posterior and the true posterior. It's very easy to show this. Perhaps this could be an exam question. Okay, since we know the KL divergence is non-negative, then we can also derive the same thing from here. So you try to decompose log likelihood into elbow plus some leftover, and use the property of KL divergence, which is non-negative, to derive this lower bound. So this is an alternative way to derive the elbow lower bound without using Jansen's inequality. So yeah, by non-negativity. Anyhow, what is the gap between the two? So this is the leftover. We want to penalize so what is the difference between the two? So if we maximize elbow, it also pushes the variational posterior towards the true posterior. So this gap between the elbow And the log likelihood is the posterior approximation gap, this guy here. Okay, so what is our optimization problem in terms of, so let's make this more concrete in terms of algorithm. All right, so we have access to n data points, which is sampled from the data distribution. So we want to increase the elbow with respect to our encoder and decoder parameters, theta and phi. Or if you want to minimize the negative log likelihood plus the KL divergence. So anyhow, the VAE loss is reconstruction loss plus KL loss. Okay, so how do we actually go about computing the objective? So we're not quite done yet. So the KL component, as we discussed, if we have this univariate Gaussian and standard normal, the KL between the two distributions simplify to this expression here in closed form. And that's obviously differentiable with respect to our encoder-decoder parameters. And that's easy. Another thing is the reconstruction term involves expectation of the z variable, z random variable under Q distribution. So how are we going to go about computing this expectation? We're just going to sample according to the Q distribution. So we're going to replace and approximate the expectation with sampling. So we're going to sample L number of samples. So given a single so to do this so this distribution expectation under random variable z. So ideally, from this distribution here, we would like to sample many many samples of z's. So we have z1 all the way to zl. And average the height here. So we're going to just take it to the extreme, set the mini batch size to 1 for efficiency. So this is aligned with the SGD, right? In SGD, you sample mini batch to approximate the gradient and just trust the gradient direction is okay and take a step, right? So here, we're going to just approximate the expectation with a single sample. You don't have to, I mean, if you have more GPU resources available, you can increase this number until it doesn't blow up the GPU memory. So one thing is we're going to replace this expectation with sample. So we want to increase the log likelihood, and if you take the log of this Gaussian distribution, then exponentiation and other things disappear into constant. So log takes care of the exponentiation, and all the nasty things like these, they all disappear into constant. So what remains is this guy here. So minimizing, we already talked about this, minimizing the negative log likelihood is equivalent to minimizing the square reconstruction error. So since we're optimizing, we're just going to replace this whole thing with MSE loss. Right? So maximizing this guy is same as maximizing this guy. But here, this term is not a function of theta. So we're just going to drop everything here because it's useless under theta. So we're just going to take this component here. So for Gaussian model, it's going to be equivalent to minimizing the MSA loss. For Bernoulli decoder, it's going to be equivalent to minimizing the binary cross entropy loss. So I think this is going to be your homework. So sounds easy so far, right? Yes. But there's one problem here. We cannot really implement this yet. Okay, so we had a number of things. Expectation, we're just going to replace it with sample mean. And KL, we locked out and had closed form solution, and it was differentiable. But there's one very important problem if you actually want to implement this, which you have to for the homework anyways. So the reconstruction term depends on sampling. So the full pipeline is you sample data, push it to the encoder, and defines distribution z given x. Then you have to sample z, and it has to get inserted to decoder, and you are able to measure the loss. But the sampling procedure is not differentiable with respect to the encoder parameter. So when in your computation graph, if you have sampling in between, you cannot backpropagate through sampling. So in and of itself, sampling layers are not differentiable. So we can compute the forward, but not the backward. Forward pass, okay, but backward pass, gradient gets blocked exactly here. But luckily, there's a solution. So for Gaussians, if you want to sample from a Gaussian with some arbitrary mean and standard deviation, you can equivalently sample from this distribution. First, you sample from standard normal, and then you multiply the standard deviation of the target Gaussian, and then you shift the mean of the target Gaussian. So sampling from this arbitrary Gaussian is equivalent to sampling from standard normal and modifying your sample so you can mimic sampling from this Gaussian. So the key idea is move the randomness into epsilon, and this guy does not depend on phi. So only this component is dependent on phi. So if you have some loss layer here in your computation graph, you can backprop through here, and here this is sampling, so you cannot backprop even if you wanted. But that's fine because we only need to backprop through wherever phi is involved. Okay. Right. So without reparameterization, this was our usual block diagram: sample data, pass it through the encoder, sample Z, decoder. This forward is fine. Backward gets stopped here exactly. But with reparameterization, you have encoder outputting mu and phi, which mu and sigma, which is all function of phi. Then we have replaced the sampling layer with this arithmetic. It's mu plus sigma times epsilon, where epsilon is STD sampling. So now forward is still fine. The backward pass you can backprop here and here naturally. Still, backprop here is blocked, but we don't care because we only need to differentiate with phi. So that's the reparameterization trick. We just needed to have massage the computation graph so it's differentiable for all the parameters that rely on phi. Okay, so how does it look like with everything combined? This used to be our objective. Now, so previously we had to sample X and pass it through the decoder and then sample Z, pass it through the encoder and evaluate the likelihood of the original data X. Now, after the change, we just sample from standard normal, and for the Z's, we're just gonna create it on the fly. So mu of X plus sigma of X times L1Y's multiply epsilon. That's gonna get inserted into the decoder, and we're gonna evaluate the likelihood of the decoder at the clean data X. Now the objective is completely differentiable with respect to the encoder and decoder and encoder parameters. Okay, so how does it look like now? In terms of the block diagrams, encoder outputs these two parameters, and using the reparameterization trick, we have a separate computation graph for sampling epsilon to provide randomness, and that allows us to sample Z and so forth. Whoa. So here is the pseudocode for the training procedure. You sample a mini batch of X, and this X gets inserted to the encoder, which outputs the Gaussian parameters mu and log variance, and you compute the standard deviation from the log variance, and you sample epsilon from STD normal, and then you construct Z by scaling the standard normal sample with STD and shifting by the mean. It gets inserted into the decoder, which outputs the decoder parameters, and you can evaluate your likelihood of the same data point here, given your constructed Z. KL divergence loss, we had closed form solution, copy pasted. So it's a sum of reconstruction loss and KL loss. And then we backprop through the KL loss. Don't worry, you're going to implement everything for the homework and teach yourself. And this is the sort of the diagram that we drew for the training procedure. So you sample clean data X, push it through the encoder, outputs two parameters, mean and log variance for Z, and this together defines distribution Z given X. And given these outputs, you can immediately compute the KL path, because KL path only is a function of whatever the encoder outputs, right? So computing the KL term does not involve decoders. So this path you can already compute. Another path is given these two parameters, you're going to do representation trick. So it's first sample from standard normal distribution, scale and shift, pass through the decoder. And this is going to define the distribution X given Z. Mu theta of Z. Sigma squared theta of Z. From then, let's use blue. You take this guy, take it here. Oops. So if I apply just a little bit more pressure, it gets the screen flickers. Okay, so here, evaluate the height here, and that's going to be the reconstruction term. So you have two components. Blue component requires you to evaluate encoder decoder, and the KL term you can directly compute after having evaluated the encoder. Okay. Combine the two terms. That's your objective, that you hit backprop. Okay, cool. So when you apply backprop, then the gradient flows here and through here, and that's the process. Okay, so what do they learn? Encoder maps data to distribution over lane variables, produces the mean and variance parameters for conditional distribution of Z given the data, and learns approximate posterity distribution. And decoder maps the latent variables to distribution over the data, and learns to generate data from latent samples. And they're trained together jointly by propagating the final loss, which is the negative elbow loss. Okay, so that's it for training. And how about generation? So for inference, we can discard the encoder. So we can just store it away and sample these directly from our design choice, the standard normal distribution, for example. Sample Z, pass it through the decoder, and then sample some data X hat from the distribution. And for visualization, people typically just they often use just the mean parameter. This guy, that's mu theta of Z. So you after having learned VAEs, you can apply it to other tasks, not just generation. Same as for AEs. You can start from X, pass it through the encoder, and then pass it through the decoder again. For example, if you trained your network on clean images, but X is contaminated, with some noise, and after you sample from this decoder, then you'll be able to get a cleaned up image, because encoder decoders are trained on clean, uncontaminated images. So you can use it for in-painting or denoising tasks, or you can just use the encoder and get a probabilistic latent representation, which then you can fine-tune your models. So once you have trained VAEs, you can do a lot of cool tasks. So since Z is very low dimensional, you can do the latent traversal. So what happens if how the generated image look like if you just slightly change Z and walk along different axes in Z's. So it turns out usually they capture many meaningful factors of variation. So for example, if you train on digits, one dimension of Z correspond to different characters, and one dimension of Z would correspond to different size of the generated fonts, something like this. And third dimension of Z might correspond to rotation angles or something like this. So just skip. So what are some, do I have qualitative figures somewhere? No. So what are some limitations? I think I had some figures somewhere. Let me see. Okay, I think ChatGPT accidentally deleted some images. So I'll open up the images. So what do I have? I mean, okay, so just give me 1 minute. Lecture 14. Okay. So what I mean by latent traversal, so let's say this middle image is your 0,0 in the latent code. You pass, for example, 0,0 to your decoder, and let's say the dimension of Z is 2-dimensional. And then along this axis, you increment the y-coordinate in increments of 0.1 or something like this, and pass it through the decoder one at a time. So you can vary in one axis and the other axis, and looks like one of the axes corresponds to rotation, one is digits or something like this. And for faces, it corresponded to degree of smile and head pose. So from left to right, from up down, this is frowning face, smiling face, and here it's turning right to left. So if you walk around different elements of Z and continuously pass it through the decoder, it corresponds to meaningful factors of variation. So this VAEs and AEs, they have to pack as much information as possible in this tight space, which is, in this case, 2-dimensional. So it's in its advantage to, in order to increase the reconstruction loss, it has to pack meaningful information. So on the Celeb A dataset, looks like if you walk along this axis, has to hair, how much hair, and this axis, I don't know, different person. Person category or something like this. I didn't notice ChatGPT. I just realized ChatGPT deleted all the illustrations. I'll change this back. Okay, that's what people usually mean when they say latent space traversal. Okay, so what are some limitations? As you saw here, it tends to generate blurrier looking images. So it's one of the downsides. The samples can be smooth but blurry compared to other models that we're going to talk about, like GANs or diffusion models. But still, learning VAEs are valuable because it has a principal probabilistic objective, and we had to talk about variational inference, which is a technique used a lot in machine learning. And it's going to get used again and again, so you better get used to variational inference. So some extensions. I don't know if we're going to have time to cover all these. Previous years we did, because we didn't have to cover so much for hands-on lectures. So some extensions, you can do richer approximate posterior if you use something like normalizing flows. So here, the idea is, can you find a one-to-one correspondence from X to Z and Z to X? So what is the mathematical tool that guarantees one-to-one correspondence? And disentanglement. So we saw that different latent space corresponds to meaningful factors of variation, like head pose and smile or something like this. But can you do better in terms of disentanglement? So how do you quantitatively measure how well these are disentangled? What's the measure that we can use reliably? Okay, once we establish that, how do we tweak the VAE algorithm so that we can increase this disentanglement metric? Because there's nothing forcing us to say, okay, Z1, Z2, Z3 they all have to, model different aspects of generative process. But that's not enforced right now. It's possible that both Z1 and Z2 are sensitive to rotation or something like this. And it actually happens. So how can we, in principle, force the model mathematically so they model orthogonal information for generation? That's the whole different area of disentanglement. So I don't know if we will have time to cover this. So in information theory, there's a concept called information gain. And in disentanglement research, this notion of information gain is used so that we can force the model mathematically to learn different concepts per each latent dimensions. And also more structured latent variables. Now, the Z's were, we modeled it as IID, standard normal distribution. And the generated distributions were also also independent, meaning the covariance matrices were diagonal matrices. But can we have more structured latent variables, but still maintain efficiency for our gradient descent-like training? Another extension is, how do we deal with discrete latent variables? So for head pose, smile, that's continuous, but there are certain latent variables during factors of variation, like number of objects and number of, light sources, category of object. These are all inherently discrete vectors of variation, right? You cannot have, I don't know, you cannot generate something that has a face of a cat, body of a person, and leg of a lion or something like this. It's discrete in order to make it realistic. And same thing for number of objects. You cannot have like 1.7 person or something like that. You either have one person, two person in the image or something like this. Same thing for a number of light sources. So previous years we covered pretty much everything on the slide, but I don't know how much time we'll have for this year. So in summary, it's a VAEs are probabilistic autoencoders with latent variables, and true posterior is intractable, so we approximate it with a neural network, and that was intuition, but the derivation was actually intuition free. We just started off from log likelihood, p theta, and then we just applied Jensen's inequality and definition of KL divergence. Or alternative approach was unpack the log likelihood equals to elbow plus some leftover, and leftover is a KL distribution between KL divergence between two distributions. It's non-negative, and we just delete it from the equation and you use inequalities with non-negativity. That's another way to derive elbow. And we also had to take extra caution because backprop in the vanilla implementation was not possible because sampling layer blocks everything. So we had to use reparameterization trick. Okay, so after training, we throw away the encoder, sample Z straight from our design, easy to sample distribution, and pass it through the decoder. And if you have some free time and you are a math nerd, then try to prove this. So if you have two distributions which are multivariate Gaussians, and KL divergence between two multivariate Gaussians have this form. And I don't know if this is going to appear again in the homework. I don't know. Yeah, we talked about disentanglement, and the very first idea that started this disentanglement work was beta VAE. This was a paper with lots of citations. Only change in their equation, they didn't even derive elbow, was this guy. You change 1 here to beta, where beta is greater than 1. And turns out, if you look at the decode equality, if you do latent traversal, it looks more pretty, meaning traversal in one domain, one dimension corresponds to one thing, the other traversal corresponds to one different thing, and it's more disentangled. It was a paper with more figures than anything, and this was the one line of change. But at first, people were surprised about the result. So this started off a line of research why this works. Mathematically, why does increasing beta to some large number encourage disentangled representation? And it was one of the foundational papers for disentanglement research. But in terms of equation, it has a single line of equation where you have beta here. All right, so that's it for today's lecture. Thanks.